For this section, I'll be talking about alcohols and their particular functional group and how we name different alcohols, and then I'll be talking about their uses. So first of all, alcohols. Here you can see a wide range of alcoholic beverages, and the most common form of alcohol is ethanol, which are in these beverages, but there are a wide range of other alcohols, and ethanol is not only used for alcoholic beverages but also for a wide range of other uses. So, what is an alcohol? Here you can see we start with a carbon chain body, which is an alkyl group, and the functional group here is a hydroxyl group, or OH. So the general formula is ROH, where R is an alkyl group and OH is a hydroxyl group. So this R could be any length of carbon-carbon chain bonding. Alcohols are actually called alkanols in organic chemistry, but alcohols are the common term for them, or the garden variety term that everyone calls alcohols. So if you see an OH group, always think it's some form of alcohol. Alkanols are derived from alkane chains. Now let's look at how we name alkanols or alcohols, and it's very systematic, so there's rules that you have to go by, and then if you see a certain compound, you'll be able to name it. So first of all, the first thing to do is to determine the number of carbon molecules in the longest carbon chain. So meth, eth, prop, bute, and so on. Give the smallest number for the position of the hydroxyl group along the chain. So whether it's in position 1, 2, 3, 4, etc. Name and number the alkyl groups and the alcohol groups. So if there are alkyl groups hanging off that long chain, you need to name where they're sitting as well. And I'll show you a few examples as we go along. And if there are more than one hydroxyl group, you use the prefix di or tri and so on, such as tetra and so on, and then you use the suffix ol. So for example, butane diol, so di meaning two alcohol groups and ol meaning it's a hydroxyl, it's an alcohol, so there's two hydroxyl groups, and butane of course is your carbon chain of 4 carbons. So now let's look at a list of alcohols, and in order of how many carbons: meth, eth, prop, bute, pent, hex, hept, oct. Okay, so methanol, there's 1 carbon, so CH3OH. So meth, and you lose the E when you've got this functional group. So whenever you see that functional group, always lose the E. So let's go to 1-propanol, for example. Meth, eth, prop, 3 carbons, an, because they're only single bonds, and ol, because there's an OH group. And with propanol, because there's 3 carbons, there's 3 positions that this OH group could be in. It could be here, it could be here, and it could be there. So we need to name where the OH group is. In this case, this molecule looks like this. The OH is at the end. Okay, now just imagine that all these other bits are hydrogens. So because it's on the end, it's on carbon number 1. So you say 1-propanol. Now if the OH was in the middle, there, it would be 2-propanol. Okay, and so on as you go down the list. So 1-heptanol has there's so many choices for the hydroxyl group to be, you have to name it. So if it's on the end, which it is here, it'll be 1-heptanol. If it was somewhere in there, you'd have to name it either 2 or 3 or 4, and so on. So that's your basic structure of how you name alkanols, and it's very systematic, so you always just follow the rules and you'll be able to name all the alcohols. So here's some examples that we can use. Here we have a structure and we have 7 carbons in the main chain. Now you may initially look at this and think, oh, 1, 2, 3, 4, 5, 6, it's hexane. No, you've got to keep going along the chain and never forget that in questions they'll try and trick you and they'll hang bits off the end. So always count that extra methyl, that's called a methyl group, a CH3. Always count that extra carbon. So there's actually 7 carbons in the main chain. So it's going to be a het, and the hydroxyl group is situated on the third carbon. So 1, 2, 3, 4, 5, 6, 7. So it's on the third carbon. So the systematic name is going to be 3 dash. So when you write these things, you have to be very strict. It's always 3, which stands for where the hydroxyl is, dash, hept for 7 carbons, an because it's an alkane, ol because it's an alcohol. Okay, so you can see that it's really quite fun naming organic compounds. So when you see cosmetics and all sorts of things with these big, long, horrible, funny names, you can always think, oh, hydroxy something, it must have an OH group, or methyl something, it must have a CH3 group, and you can have a lot of fun with them. So another example, in this one we have 5 carbons in the main chain, but this time we have 2 hydroxyl groups, okay, one here and one here, and they're in position 2 and 3, okay, so 1, 2, 3. So our systematic name is going to be 2, 3, and when there's 2 of them, we write it 2, 3, dash, pent for 5, pentane, and when we have a diol, we keep the E, okay? So the di means 2 hydroxyl groups, diol, okay? So when you've got a diol, always keep the E. So let's look at properties of alkanols. Here's a simplistic drawing of an alkanol with an alkyl group here, and here's our OH group, and similarly here again. What we have is a non-polar chain. The alkyl group is non-polar and the OH group is polar. So in an alcohol you have a non-polar and a polar section, and that's because the oxygen here actually has 2, that's how we draw it, 2 lone pairs of electrons. So we have polarity here between the hydrogen and the oxygen, and this brings about all sorts of interesting properties for these compounds. So what happens is they can form hydrogen bonds with other alkanols. So in between these two, there's hydrogen bonds between the oxygen and the hydrogen of both of these alcohols. And hydrogen bonds are actually really, really strong. In alkyl groups, because they're non-polar, they only have dispersion forces, which are quite weak. But in alcohols, they have hydrogen bonds, which are very strong. So alkane and alkene counterparts of the alcohols, such as butane, methane, ethene, ethylene, only display dispersion forces, okay? But alkanols display hydrogen bonds. So more energy is actually required to overcome strong hydrogen bonding in alkanols because the bonds are stronger. Hydrogen bonds are always a lot stronger than dispersion forces. So alkanols have a higher melting point and a higher boiling point because of these hydrogen bonds. And they're a lot higher than their alkane and alkene counterparts. So let's look at ethanol, the most common of all of the alcohols. There's hydrogen bonding across the hydroxyl group. It has a higher melting point and boiling point than ethane and ethene. And it has the polar hydroxyl group, which allows dissolution in polar substances. But it also has the non-polar carbon chain, which allows dissolution in non-polar substances. So ethanol can dissolve both in polar and non-polar substances, which makes it a fantastic solvent, which is what its main use is, actually. So, ethanol as a solvent. Ethanol can be dissolved in both polar and non-polar substances. So this is ethanol, meth, 2 carbons, anol with the OH group. And this is our non-polar section in yellow, and this is our polar section in blue. And what we have here is water coming along. So for example, we're diluting ethanol in water, and water will come along and you'll get hydrogen bonding between the water and the ethanol. So as I said, it's a very versatile solvent. So as a solvent, some examples of where they use ethanol as a solvent. For example, in industry, all sorts of industry such as mechanics, carpenters, builders, all sorts of industry uses will use ethanol. In the laboratory, every chemical laboratory, it is the most common solvent is ethanol. You will find tubs and tons of bottles of this ethyl alcohol. That's actually another name for ethanol, is ethyl alcohol. It's also used for the pharmaceutical industry to make drugs, and it's used to make cosmetics. So let's look at the types of alcohols, and this also helps in our naming. First of all, we have a primary alcohol. Now this R group is just another alkyl group, okay, another carbon chain. That's our primary alcohol. Now one carbon and two hydrogen atoms are bonded to the carbon atom, which is joined to the hydroxyl group. And R is your alkyl group. So that's your primary alcohol. Then we have our secondary alcohol. And this is our secondary alcohol, where we have two different R's. So when you have two different alkyl groups, we denote that with R and R dash, meaning that they're different. Now if R was the same carbon chain, you would just write R, C, OH, and that would just be R. It would still be a secondary alcohol, but it just means that that group is exactly the same. So that's showing you that the two R groups are actually different. So it has two carbon and one hydrogen atom bonded to the carbon atom, which is joined to the hydroxyl group. And finally, okay, and R is another alkyl group. And finally, tertiary alcohols, where you have three different R groups. So you have three carbon atoms bonded to the carbon atom, which is bonded to the hydroxyl group. So here we have three different R groups. Okay. So let's look at bonding in alcohols. The strength of the hydrogen bonding is proportional to the degree of hydroxide group exposure to other molecules. So the hydroxide group is more exposed in primary alcohols. So if you think of, let's say, propanol, one propanol, hydroxide is at the end, so it's more exposed to other things. Okay, if you think of 2-propanol, where the OH is here, it's less exposed because it's got these carbons around it. Okay, so the OH group is least exposed in tertiary alcohols. Okay, and this again leads to the different properties of either primary, secondary and tertiary alcohols. So primary alcohols have a higher melting point and boiling point because they undergo more hydrogen bonding. Therefore, there's more molecular forces to be overcome for there to be a change of state. Okay? So to sum up about bonding in alcohols, primary alcohols have a higher melting point and boiling point. Secondary alcohols follow with a lower MP and BP, melting, boiling. And tertiary alcohols have the lowest of all three. Okay? So that sums up about naming alcohols and a few examples to help you along. So we'll now look at a few questions. Question 1, name the following compounds. Now this has 5 parts, A through to E, and we'll go through them one by one. So how do we name this compound? First of all, rule number 1, count the carbons. So count the carbon backbone. 1, 2, 3. So it's meth, eth, prop. So we start with prop. We know there's an OH group, so it's an ol. And then you put it together, and it's 1-propanol, because the OH group is right at the end. So it's on carbon number 1. Now part B, we have a structure instead. Name this compound. Count the carbons. 1, 2, 3, 4. So meth, eth, prop, bute. So bute. Alcohol group, yes. So it's an ol. Where's the group? 1, 2, 3. But with these compounds, you can go backwards and forwards. So instead of always starting on the left, this might trick you sometimes, don't be tricked. Instead of starting on the left and thinking, oh, it must be 3-butanol, it can go that way too. So you always have the least number of carbons from each end. So from the right-hand side, it's actually 1, 2. So that's 2-butanol. Part C, let's name this compound. Count the carbons. 1, 2, 3, 4, 5. Oh, no. 1, 2, 3, 4. Okay. It's a bute because there's 4 carbons. How many OHs? There's 2 of them, so it has to be a diol. And then we have to look at the position. Carbon 1, carbon 2, carbon 3, and carbon 4. Where are the hydroxyl groups? Position 1 and 4. So it might be easier if I actually draw this for you. OH, OH, where the rest of them are hydrogens. So 1, comma, 4, dash, bute for 4 carbons, ane, because there's no double bonds, or because it's an alkane, and di, because there's 2 hydroxyl groups, and finally ol, because of the hydroxyl groups. And part D, name this compound. So first of all, we count the number of carbons in the backbone, so there's 3 of them, and then we have a look at the different functional groups which are on this compound. Now, the name of this compound is 2-methyl 2-propanol, and the reason for that is our systematic way of naming. So, meth, eth, prop, so it's going to be prop. It's an alkane, so an. Ol, because we have a hydroxyl group. And this compound is actually a secondary alcohol. Now, we write secondary in chemistry as 2 with a little degree sign above it, and this means secondary. So it's a secondary alcohol because of this methyl group here. So we have to name where that methyl group is by counting the carbons, just in the same way as we do for the hydroxyl group. So where is the methyl? It's on carbon 2. So we start with the methyl, 2-methyl, and then where's the hydroxyl? It's also on the second carbon, 2-propanol. So that's how we would name that molecule. Part E, so name this compound. So once again, start by counting the number of carbons. So there's actually 10 in there. And don't forget, there might be things hanging off the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to have dec in its name. And then we look for other functional groups. Okay, we have a hydroxyl there, and we have a hydroxyl there. So this compound is named 2,8-decane diol. Why? Because we have 2 hydroxyl groups, we have to put in di and ol for the alcohol group, and the backbone is decane because it has 10 carbons. It's an alkane, so it's ane. And the 2-8 refers to the position of the hydroxyl groups on this compound. So if you just sequentially go through and pick where the hydroxyl group is or the other functional group, count the carbons, just go through those rules. If you follow those rules, you can name just about any alcohol, or for that matter, most organic compounds. As long as they're not too complicated, you won't have a problem. Question 2, which of the following is the molecular formula for 3-hexanol? So looking at 3-hexanol, hex tells us there's 6 carbons. So first of all, we can rule out D. Ol tells us there's an OH group. Okay, great. And 3 tells us where the hydroxyl group is. So the structure of this compound, the hydroxyl will be on the 3rd carbon. 1, 2, 3. So now all we have to do to name the molecular formula is to count up all the different substituents of this compound. So there's going to be 6 carbons, so C6. And if we go through and count them, you'll find that the answer to this question is C, where we always list the carbons first, then the hydrogens, then the oxygens. So for these 2, they're ruled out because they don't have the right number of hydrogens for a start, but they might try to trick you by writing an OH group at the end of the formula. We don't actually write it that way. We actually group the hydrogen of the hydroxyl group with all of the other hydrogens. Okay? Question 3, what is the IUPAC structural formula for 2-butanol? Okay, so meth, eth, prop, but, there's going to be 4 carbons. So 1, 2, 3, 4, 5, straight away we can rule out C. Okay, an, which means it's an alkane, so we can straight away rule out the double bonds are an alkene. So by process of elimination, our answer there is going to be B. And it is because the hydroxyl group is on carbon number 2. So that's our answer for question 3. Question 4, which of the following is not a correct statement about alkanols? So I'll start with the answer and I'll work backwards. The functional group for alkanols is the hydroxide ion. Okay. Now this is incorrect because the functional group of alkanols is called a hydroxyl group, as I've been discussing in this lesson, not the hydroxide ion of ionic compounds. So that's your hydroxide ion with a negative charge. So that is incorrect. And all the others are actually correct. So the general formula for alkanols is CnH2n plus 1 OH. So for example, if we make N equals 2, C2H5OH, draw it, you've got ethanol. Okay, so that fits. Part C, the carbon atoms are numbered so that the carbon with the OH attached has the lowest possible number. Yes, that is true. And D, alkanols are polar compounds. Yes, that is true. So our answer for question 4 is B. Finally, question 5. Explain how ethanol can be used as a solvent for both polar and non-polar substances using a specific example for each and a labelled diagram. So, ethanol can dissolve in polar substances such as water and also in non-polar substances such as iodine, which is actually a brown liquid at room temperature. It contains a polar hydroxyl group that can form hydrogen bonds with polar substances. So that's its polar end, is that hydroxyl group. It also has a non-polar hydrocarbon chain that can interact with non-polar substances through dispersion forces. So ethanol has both dispersion and hydrogen bonding. So here's our diagram to show the polar and non-polar sections. So here we have our polar hydroxyl group with hydrogen bonding. Whenever we write hydrogen bonding, we always do a dash, dash, dash like that to show that it's not a true bond, but it is a strong interaction. Okay, so that's what those dashes are. So you've got your polar part over here in white, and over here we have our non-polar chain. So that's our hydrocarbon chain there, and here we have another dash. These are dispersion forces, and this is iodine here, I bonded. So that's how you would draw the diagram for that question. So that wraps up our questions for today, and also our theory about alcohols. So I've introduced to you the fact that alcohols have a hydroxyl group or an OH, and that's our functional group. And I've spoken about the fact that, as we can see in this diagram, alcohols are both polar and non-polar, which makes them very useful for a wide range of uses. And in our next lesson, I'll be discussing the various reactions of ethanol.